multiple sclerosis is the most common autoimmune disease affecting the central nervous system. Its clinical presentation is extremely heterogeneous, with the immune system damaging the myelin sheath of neurons at various sites throughout the body. While the disease worsens steadily over time for some patients, most patients experience these autoimmune attacks sporadically as part of relapses, followed by a full or partial recovery. This complex, irregular, and heterogeneous clinical manifestation of the disease makes it very challenging to accurately measure the effects of treatments in clinical trials. Now, the most straightforward approach to increase the power of a trial is to enroll more patients. But this is very costly and time-consuming. So to summarize, it would be desirable to be able to run clinical trials with reduced numbers of participants in order to increase efficiency, reduce costs, and enable more studies to be conducted in MS. In turn, patients would have the opportunity to participate in more clinical trials, so efficacious treatments for this population could be identified faster. So our approach reduces the number of patients required to enroll in a clinical trial while maintaining statistical power and preserving type 1 and type 2 error rates. A clinical trial design, known as a twintelligent RCT, follows regulatory guidance on incorporating covariates into an ANCOVA analysis. Namely, one should include baseline covariates that are predictive of a patient's outcome. The more predictive the covariate, the greater the power it contributes to a statistical analysis. What we do is we leverage machine learning and historical data to predict the patient's outcome from their baseline measurements. We call these predictions digital twins, and they form a near optimal covariate to explain away the variance of the outcomes, drastically increasing the power of the statistical analysis while preserving the type 1 error rate. Our aim is to build a model of MS progression which can predict the outcomes in control populations specifically to support the primary and secondary analyses of clinical trials. And to support the many possible primary and secondary analyses, it's crucial that our model make comprehensive clinical predictions, including all the major endpoints, EDSS, functional scores, relapse events, etc. So fully comprehensive model. So we used the data from nearly 2,400 patients in the control arm of past clinical trials to train and validate a machine learning model which predicts the progression of MS. So these data include patients with the 3 primary subtypes of MS: relapse-remitting, secondary progressive, and primary progressive. What we did is we split the subjects in the data into 2 portions, so training portion and a held out validation portion. A machine learning model was trained on the subjects in the training portion. Once trained, the model was used to predict the outcomes for those subjects in the validation portion. These predictions are called digital twins, and we compared their accuracy against the actual outcomes. So it depends on the endpoint one is interested in, and also the population one is studying. So for example, for continuous endpoints, such as the change in EDSS or the relapse rate, the correlation between the digital twins predictions and the actual outcomes is on the order of 0.3. This is strong enough to provide real gains in efficiency to a clinical trial. For binary and time to event endpoints, such as confirmed like CDI or CDP, time to relapse or time to CDI, the AUC or C index of the predictions is a better measure of the accuracy than correlations, though it's measured on a different scale. And we found that the AUC or C index of the digital twins predictions for these endpoints tends to be on the order of 0.7, which is again strong enough to provide real gains in efficiency to a clinical trial. But let me step back and translate these numbers to actual efficiency gains. So using a held out data set, we found that we were able to reduce the control arm size by approximately 20%. This depends again on the population being studied and the particular primary endpoint of interest, but we welcome the opportunity to evaluate the performance in cooperation with a partner in retrospective or prospective studies. Digital twins can be used in several ways to improve the efficiency of clinical trials. So stepping back to, say, the design stage, they can be used to simulate the outcomes for the control group across endpoints to aid in strategic decision-making, such as understanding the effects of inclusion or exclusion criteria, selecting cohorts or subgroups with specific types of progression, or to support sensitivity analyses. In early phase trials, David Walsh and his collaborators have shown that they can be incorporated into a Bayesian analysis to drastically reduce the control arm while maintaining power and suitably limiting type 1 errors. But most significantly, as I said before, digital twins can improve the efficiency of trials supporting regulatory decisions, reducing the required size of the control group while maintaining strict type 1 error rates. In this scenario, going back to it, the patient-level predictions provided by the digital twins are entered into an ANCOVA model as a covariate, increasing the statistical power by explaining away the variance. We're ready to do that, and we want to enter into partnerships to use these in trials, both retrospective ones and prospective ones.